Hello. I apologize. I am sick. My son is sick, and I'm losing my voice, so hopefully you can hear me. This section corresponds to Chapter 7, Section 6, and it deals with polynomials. So all of these PowerPoints, again, available in Canvas. Basic terminology, a term or a monomial is defined as a number, a variable, or a product of those. A polynomial is the sum or difference of multiple terms using non-negative integer exponents, which correspond to a degree. So it has some examples there. A polynomial could be x squared minus 9, 2x plus 5, or 1 minus x. Like they're all polynomials. So we have to have a integer as an exponent. Can't have any negatives or non-negative integers. Yep, can't have any negative exponents, fractions of exponents, nothing like that. The degree of the polynomial corresponds to the term with the highest degree. So for example, we have here 4x squared y cubed z. We would add all of those exponents together. 2 plus 3, z doesn't have one, but it's imaginary 1. 2 plus 3 plus 1 is 6. If I said, what is the degree of a polynomial? That's 3x to the fourth minus x cubed plus 2x plus 8. The degree of this polynomial comes from the biggest exponent, so we would say that the degree here, when it's a polynomial of sums or differences, the degree there is 4. So you don't want to combine the exponents for a polynomial, just say terms specifically. A trinomial is a polynomial with 3 terms. A binomial is a polynomial with 2 terms. And we'll just use that language throughout. So if it says factor the trinomial, we know that it would have 3 terms, and it will look that way. Whenever we add or subtract polynomials, we always combine like terms. Like terms have the same exact variables, same exact exponents. So for example, if I said 8x squared and negative x squared, those are like terms because they both have an x and they have the same exponent. If I had something like 8x cubed and 8x squared, doesn't matter about the coefficient, we check, they are not like terms because their exponents are different. If we were asked to add or subtract, again, we combine like terms. So here I have a 2x cubed. I'm plussing with another x cubed. So I want to add those together. And I would say 2 plus 6, we just add the coefficients, would give us 8x cubed. So notice we don't change the variable or the exponent. Then we're going to combine our x squareds, 3x squared plus negative, this is like an imaginary 1. 1x squared is 2, so it's positive, so positive 2x squared. We have our linear term, our x's. We have negative 7 plus 2, so we get negative 5x. Then finally, we have a 1 plus 5, and we know that that's 6. Plussing because it's plussing in between. For subtracting, if you like the idea of keep, flip, change, if you remember that from high school algebra, you could keep this the same, flip this, and then change all of the symbols in your other set of parentheses. Or I just sort of sit there and just subtract. So I have 4m to the fourth minus 3m to the fourth. 4 minus 3 gives me 1. I don't really need to write that, so I'll just write m to the fourth. You don't need to put the 1 in front. Next, we have m squared minus negative m squared. So we have a negative 1 minus negative 1. When you subtract negative numbers, you just have to remember to turn it into addition. So it'd be negative 1 plus 1m, which is 0m squared. We don't have to write that. If it cancels out, we don't have to write it. Then we have our linear term, negative 7 minus 1m gives us negative 8m's. And finally, 9 minus negative 3. When we do 9 minus negative 3, we just have to be careful. You can always use a calculator because it becomes 9 plus 3. So we know that this is 12, positive 12. And those would be our answers. When we multiply polynomials, that's where we're going to apply our properties of exponents that we talked about this past week on Tuesday. So that way we can actually simplify and solve. A lot of times we'll distribute. So what we'll do here is, this is multiplying polynomials vertically. I just go through and I distribute. So I'm going to take 3x squared and I'm going to multiply every single term in my second parenthesis. I have 3, it's a trinomial, by 3x squared. So I'm going to take 3x squared times 5x cubed. 3 times 5 gives me 15. When we multiply, we add exponents. So x to the 5th. Then I'm going to take 3x cubed times x. 3 times 1 is just 3, so positive 3. I have x squared and I'm adding it to x to the first power, which is x cubed. And then 3x squared times positive 2 gives me positive 6x squared. And then I'm going to distribute all of the other terms inside of the next parenthesis. So x times 5x cubed, which gives me, I'm just going to write it below, 5x to the 4th. X times x gives me positive x squared. X times 2 gives me positive 2x. It's a lot of things there, so I'll go underneath this time. Negative 2 times 5x cubed gives me negative 10x cubed. Negative 2 times x gives me negative 2x. And negative 2 times 2 gives me negative 4. And then what I do is I go through and I combine like terms. So for example, I look and I start off with my biggest degree and my largest degree, which is my biggest exponent. 15x cubed, or at 15x to the 5th, excuse me. I don't see any other x to the 5th, so I just rewrite it, 15x to the 5th. I do have an x to the 4th. It's my only x to the 4th. It's a positive 5, so I'm just going to rewrite it, positive 5x to the 4th. So we take our 3x cubed, our negative 10x cubed, that gives us negative 7x cubed. We have these x squareds here, so we add their coefficients, 7x squared. We're going to add our linear terms together. A positive 2 and a negative 2 cancel. We don't have to write plus 0. And then finally, we have a negative 4, so we put that there. We double check if we have any other like terms. We don't. That is our answer. You can write everything horizontally or vertically. Sometimes it matches up vertically, so it's easier to do that way, but it's up to you. The FOIL method is what I just did. So I'm like, the FOIL is just binomial times a binomial, but all you do is you just distribute. So you can pause the video, try this one, and I'm gonna put up my answer. So try it, pause the video and try it, do mine. If you did yours and you're unpausing the video, that's my answer. So what we can go through and do is obviously we can multiply polynomials, but like how do I take this and turn it into this? When we do that, typically with multiplication, we talk about division, undoing multiplication. Polynomial division, you have done it before, you know what I'm talking about. It takes time, takes a lot of time. There's a lot of trial and error to it in order to find these, like a lot of trial and error. Instead, what we can do is sort of a shortcut, like to save us time if possible, we can factor polynomials. So that is where we're going to lead into here. We have what is called a difference of two squares. You can multiply them together. Like say if I had something like x plus 3 and x minus 3. I already know this situation is going to work out. I can multiply through, but I can take x times x. I know that becomes x squared minus 3 times 3 is 9. It works out. You can multiply, FOIL it through. It is going to work out. It's a difference of two squares. So what we're going to head into is we can be given this, and we can work our way backwards. For example, if I gave you x squared minus 16, we can work our way backwards like we have over here with our parentheses, break apart x squared into x and x, just like over here. One clearly got a plus, one got a minus, and really 3 times 3 gave us 9. Square root of 9 is 3, square root of 16 is 4, because 4 times 4 is 16. That would be our answer. So that's, again, where we're heading. So here, if I'm asked to multiply these, I already know since they look identical, one's a plus, one's a minus, I just have to multiply these first pieces. 4 times 4 is 16, p squared. 9 times 9 is 81. It gets a minus in between, and that's done. Again, I could give you this, and we can work our way backwards with squares with square roots. Square root of 16 is 4. Square root of p squared is p. Square root of 81 is 9. One gets a plus, one gets a minus, and we're done. We also have some squares of binomials, like where these special products are. I don't think most people remember them. I honestly don't. Well, I do, but it's because I'm a math person. If I wasn't, I would never remember these. Really, what I always tell students is if you see x plus 1 squared, just know that it's x plus, like even if 1 doesn't make you feel comfortable, let's do 9. X plus 9 times x plus 9, and then you FOIL, distribute, and you get an answer. You don't have to memorize these. Even if it's x minus 8 squared, you would just take x minus 8 times x minus 8. What you never want to do is distribute an exponent across multiplication or subtraction. That's a huge no-no. It's like math voodoo. You never do that. You never distribute a exponent across addition or subtraction. You don't have to memorize these. Just know it's x plus 9 2 times, FOIL it, distribute, multiply through, and you'll get your answer. So factoring, I've already alluded to this. Factoring is what undoes multiplication. Similar to division, but it will save us a lot of time with polynomials. Whereas division, it can be really time consuming. So this will save us a lot of time. And there are really big applications. Like you might be like, who really cares about dividing polynomials? Who really cares about factoring them? Again, a lot of these pieces in algebra seem very disconnected, but if you go into upper level mathematics, you will see them in calculus. You'll see why they're important. They deal with functions where they're crossing the x-axis. That can be important in real concepts in terms of even like dropping a ball. Like if I go out my window right now and throw my pen down, I can use this idea of factoring, this idea of solving, dividing, whatever the case is, polynomials, whatever strategy I decide to use in order for me to determine how long it's going to take for my pen to hit the ground. Or what's the wind like? What's the amount of friction like? Things like that. So these have a lot of applications. You just don't necessarily see them when you're doing them the first time. You're like building the skills. So potentially you might use them later, but they're all around us and we use them constantly. So the first thing that we can do anytime we factor, we always want to first check if we have a GCF because it will save us a lot of time. A greatest common factor is something that we can divide both of them by numerically and any variables that they have in common. So here's our example. Numerically between 8 and 12, I know I can divide them both by 4. I know that. If you're not sure and you have a certain type of calculator, there is a way on the calculator for it to pull the GCF from 2 numbers. The TI-84s will do it, the Inspires will do it. A lot of the scientific ones, some will, some of them won't. So it just depends on a calculator that you have. Variable-wise, they both have an x. This term has 3 x's, this one has 2, so I know they both have at least 2 x's in common. Rule of thumb for GCF, you take your variable in common, take the lowest exponent. And then what we do is we put a parenthesis to figure out what's left over. We're basically undoing the idea of the distributed property. Like we're doing the opposite of the distributed property. We're going to divide everything by that GCF 4x squared. 8 divided by 4 is 2. We had 3 x's. We took 2 away. We can subtract. We're left with x. So the first power is x plus 12 divided by 4 is 3. Our x squareds cancel. That is our answer. You can always double check yourself. by distributing. So I could distribute, I'll just show that really briefly. And I would distribute and multiply through, and I'd be like, oh yeah, you know what? That does give me what I started with. Done, we know we did it correctly. But this would be the factor GCF. That would be the answer. This is just my check. So this factor is the inverse of multiplying. Again, it's sort of like the idea of dividing, kind of. It's a little bit different, but it just will save us a lot of time. Whereas if we go through and divide polynomials, it can be cumbersome and can take some time. If we're asked to factor trinomials, you can do it whatever way you remember doing in high school. My high school teacher taught me how to guess and check. I don't think that's a really good strategy, especially teaching algebra 2 where this is taught for so long. Yeah, it's not a good strategy. So I'm going to teach you my way. Do whatever way you want. Whenever I go through and I do this, I look, it's a trinomial, and I'm going to go through and I multiply. I take 6 times -5 and I write it down. So -30. So my goal is to figure out, and I write it in like a T-chart, what multiplies to -30 that adds to my middle number, -7. This is the adding part. For time purposes, you can pause and sort of think about it. I'm going to write the answer. -10 times 3 gives us -30. -10 plus 3, it has to be the same two numbers, gives us -7. So what I do at that point is I rewrite my polynomial. I keep my leading coefficient, my leading term, 6x squared. Gonna leave some space. I keep my constant. And what happens is I'm creating a situation where I'm breaking my middle term into an equivalent. -10x and +3x. And there's a reason that I'm doing this. Because then what we're able to do is we're going to factor it. We're going to factor it by what we call grouping. And I'm going to group these into two groups. When and it doesn't matter, the placement of the -10 and 3, they could be backwards. Like I could put the 3 here and the -10 here, it does not matter. Then I'm going to pull out GCFs in each of my groups. So the GCF between 6x squared and -10x is 2x. I'll divide just those two values by the 2x, and I rewrite what's left over, 3x squared minus 5. In my second group, 3x and -5, they don't have a GCF other than 1, and I'm going to pull out a 1, positive 1. I'm just going to rewrite it, 3x minus 5. Like there's nothing that 3 and 5 have in common besides 1. And if it's a positive, which it is here, I don't want my signs to change. It's going to be 1. And I actually rewrote, this is incorrect. This should just be 3x. I wrote that incorrectly. Notice our parenthesis values are exactly the same. And at this step, they should be. If they're not, we did something wrong. So what happens is since they're exactly the same, I pull those out, 3x minus 5 just once. And then whatever I have left over, which is 2x and plus 1, I rewrite in another parenthesis. And that is how we factor trinomials. If you have another way to do it, feel free to do it that way. It's just the way that I know from constantly doing this with students for over 10 years that this is one way that works really well every time. There's no guessing and checking involved. The next one, if you have a perfect square trinomial, something like this in this type of format, what we're able to do, and I don't think a lot of people recognize them. I always tell people like, look, if these are perfect squares, like 1, 4, 25, 36, 144, I don't think a lot of people recognize that this is 13 squared and that maybe you recognize this is 4 squared. If they're perfect squares, multiply those together, like take 13 times 4 and then multiply it by 2 and see if it works out. I don't think that that's natural for a lot of people. But if it did say factor the perfect square trinomial, if that's what the directions were, then what I would do, and you can see on the last screen, is I just go through and we just take it to Square root of 69 is 13. Break your x. This is a plus, this is a plus, this is a plus, so I put plus. Square root of 16 is 4 squared. If it was just on a general, like, factor this polynomial, and it didn't say it was perfect square trinomial, I don't think a lot of people would recognize it. And you could do, potentially, the method that I showed with the trinomial before. It'd be really large numbers to work with, but it would still work the same. You don't have to remember and do it this way. If there are a difference of squares, alluded to this before, where it's a difference, it's a binomial, they're perfect squares. It's very simple to do. We'll have two sets of parentheses, and we take the square root. The square root of 25 is 5. That in both, we break apart k squared to just k. Square root of 4 is 2. One gets a plus, one gets a minus. It does not matter if you put the plus or minus first and whatever second. That would be our factorization. So differences of squares are really easy to recognize and they're really easy to do. Even here, if it says factor the difference of squares, I start off 16(1) perfect squares. Even though this isn't at 2, it's an even exponent. As long as it's an even exponent, it's technically what we call a perfect power, so we're able to do it. Square root of 16 is 4, so I have 4x. I break my exponent into two pieces, so 4 divided by 2 is 2, so 4x squared. The square root of 1 is 1, so I put a plus and a minus. What we have to be careful of is we also have another difference of squares right here, because 4 and 1 are perfect squares. So I would factor it to 2x plus 1 and 2x minus 1. And all I want to be sure is if I'm continuing to completely factor, that whatever I had originally also hangs along the outside for the ride. So you can keep going. There might be a situation where you can't, like with an even exponent, like if this was a 6, we could not keep going. But for this, you can. This one just works out that you can. And that is it. So again, I apologize for not being able to actually hold a group session tonight. If you have any questions, comments, concerns, feel free to message me in the chat, like on Teams, or you can email me. Please work on the homework for this section and come on Tuesday with any questions, concerns that you have. The homework is due next Thursday, February 1st, and that is when we'll take our exam on all of that we've done so far, everything in algebra.